What if I told you the AI explosion didn't start in a polished lab in 2010, but in a cramped garage where engineers feared coffee spills more than future breakthroughs? Imagine watching a friend tinker with a clunky computer while juggling mugs of espresso. That was the real atmosphere. In the late 1970s, a handful of MIT alumni assembled a machine that could solve algebraic equations faster than any human. At the time, few imagined that this modest expert system would spark a chain reaction, turning a niche curiosity into a worldwide industry worth hundreds of billions. The story begins not with a flawless algorithm, but with a risky gamble, venture capitalists ready to pour millions into a field many still called science fiction. Those early funds bought the first massive mainframes, hired scientists who felt more at home with punch cards than PowerPoint, and ignited a rivalry that would dominate the next decade. As the Cold War sharpened, the US government spotted a strategic edge in machines that could think, even if only a little. By the time the first commercial AI product hit shelves, a hidden network of innovators had already laid the groundwork. This unlikely birth gave rise to the AI engines that now drive our smartphones, suggest movies, and even diagnose disease. So, what conditions turned a handful of daring experiments into a global revolution? In the early 1980s, university labs resembled factories of imagination. At Stanford's AI lab, a group of graduate students huddled over a Sun workstation, feeding it knowledge about chess moves. Across the country, Carnegie Mellon's robotics crew taught machines to crawl through simple mazes with clunky wheels and whirring motors. What united them was a shared conviction that knowledge could be encoded, that rules could be translated into code, and that computers could someday outpace human intuition. Funding arrived as a patchwork of federal grants, defense contracts, and a few bold private investors hoping for military advantage. Yet progress crawled, hardware costs were astronomical, and memory lingered in kilobytes, a fraction of what today's smartphones hold. Still, breakthroughs emerged, the first natural language parser that could understand limited sentences, and early neural networks that mimicked brain cell connections with only a few dozen neurons. These modest wins proved machines could learn, even if they stumbled over basic tasks. As the Cold War thawed, pressure to outpace Soviet research surged, prompting the US government to boost its AI stake. This cash infusion forced labs to think bigger, push hardware limits, and start collaborating across state lines, setting the stage for a seismic shift in how AI would be funded and deployed. How did a single corporate gamble later turn these laboratory dreams into marketable products? By the mid-1980s, a new class of software called expert systems burst onto the scene, promising to capture the decision-making prowess of specialists, doctors, geologists, even financial analysts. One of the most famous, Exioen, was born inside a DEC data center, tasked with configuring complex computer orders for customers. The program encoded thousands of rules from veteran engineers, turning weeks of human labor into minutes of automated computation. This success was more than a technical curiosity, it proved that codified expertise could generate real profit. Companies rushed to replicate the model, launching products like Mycin for diagnosing blood infections and Dendral for chemical analysis. Investors, noticing the massive cost savings, poured capital into AI startups, igniting a speculative bubble reminiscent of the dot-com frenzy a decade later. Yet the excitement masked a fundamental snag: the rules had to be written by hand, a painstaking process that didn't scale beyond narrow domains. Still, the market response was undeniable. By 1990 the AI industry was generating billions in revenue, and businesses began to envision a future where machines could shoulder routine, high-stakes decisions. So, when did computers finally grow strong enough to learn those rules on their own, shifting the paradigm from manual encoding to self-directed learning? In the early 1990s, a small research group at the University of Toronto dared to revisit an old idea: artificial neural networks that could adjust themselves through experience, much like a child learning to ride a bike. Led by Geoffrey Hinton, they introduced backpropagation, a method allowing networks to fine-tune internal connections by comparing predictions to actual outcomes. At first, the approach seemed academic, confined to ivory tower papers and modest grant budgets. But the breakthrough lay in its scalability. Once the algorithm was set, the network could ingest massive datasets and improve without a human rewriting rules. The real catalyst arrived in 1997 when IBM's Deep Blue defeated world chess champion Garry Kasparov. While Deep Blue relied on brute force search, the public imagination linked its victory to thinking machines. Suddenly, investors sensed that learning-based AI, no longer shackled by handcrafted rules, could tackle problems previously deemed impossible. Startups like Netscape's early recommendation engine began experimenting with collaborative filtering, using user behavior to predict preferences, a primitive form of what we now call machine learning. At the same time, graphics processing units originally designed for video games proved remarkably efficient at the parallel calculations neural networks demand. This serendipitous hardware-software marriage set the stage for rapid acceleration, as researchers finally could train deeper, more sophisticated networks. How did these technical advances fuse with a cultural shift to turn AI from a niche research topic into a mainstream commodity? When the World Wide Web opened to the public in the mid-1990s, it unleashed a torrent of user-generated content, a digital goldmine for any system hungry for data. Suddenly, search engines needed to index billions of pages, and e-commerce sites collected purchase histories from millions of shoppers. Companies like Amazon and Google recognized that the key to harnessing this information lay in algorithms that could learn patterns without explicit programming. Google's PageRank, for instance, treated links as votes, allowing the search engine to rank results based on collective human judgment rather than pre-written criteria. Simultaneously, Amazon's recommendation engine started suggesting books based on previous purchases, quietly applying early machine learning to boost sales. This massive, real-world dataset gave AI a new playground. Instead of training on small, curated sets, models could now ingest the noisy, chaotic reality of human behavior. The scale was staggering. By 2005, Amazon's catalog featured over 18 million products, each linked to countless customer reviews and ratings. Training a model on such a tapestry meant predictions became startlingly accurate, and the business value skyrocketed. The moment also revealed a paradox: the more data fed to a system, the less need there was for human-crafted rules, yet the risk of bias and privacy concerns grew. This tension spurred a wave of regulation and ethical debate, foreshadowing today's discussions about AI fairness. As datasets swelled, another force gathered momentum: the democratization of powerful computing through cloud services, which made sophisticated AI tools accessible to anyone with an internet connection. What hidden consequences would this data explosion unleash on society and emerging AI-driven enterprises? Most people think AI's power springs solely from sophisticated algorithms, but a handful of obscure breakthroughs reshaped the field. First, the invention of the ReLU activation function in 2009 seemed trivial, a simple mathematical tweak that let neural networks train faster and avoid vanishing gradients. In practice, ReLU turned deep networks from sluggish learners into lightning-quick recognizers, paving the way for the massive models we see today. Second, a modest project at the University of Montreal introduced dropout regularization in 2014, a technique that randomly disables neurons during training. This counterintuitive move prevented overfitting, meaning models could generalize better to new data, a crucial step for reliable real-world applications. Finally, transfer learning, taking a model trained on one massive dataset and fine-tuning it for another task, reduced the need for enormous labeling efforts. Suddenly, a single image recognition network could be repurposed to diagnose medical scans with minimal additional data. These three seemingly small innovations acted like hidden levers, amplifying AI's capability without a proportional surge in computational power. They sparked an explosion of practical tools that even small startups could wield, accelerating adoption across industries from agriculture to finance. Have you ever used a smartphone filter that seemed to know your face? That's the ripple effect of these hidden advances moving AI from research papers into everyday hands. Walk into any grocery store today, and behind the automatic doors sits an AI system analyzing foot traffic, adjusting lighting, and predicting inventory needs before shelves run dry. On the highway, navigation apps reroute you in real time, using machine-learned traffic patterns that were impossible a decade ago. In hospitals, radiologists rely on deep learning models that flag anomalies in X-rays with an accuracy rivaling seasoned specialists, cutting diagnostic time from hours to minutes. Even your smartphone's voice assistant, whether you call it Siri, Alexa, or Google, interprets natural language through neural networks trained on billions of spoken phrases, turning casual chatter into actionable commands. These examples illustrate how AI, once a far-off curiosity, now operates silently in the background of daily routines, trimming costs, boosting safety, and creating new conveniences. Economically, the impact is profound. A 2022 study estimated that AI contributed roughly $2.6 trillion to the U.S. gross domestic product, a figure comparable to the combined output of the automotive and aerospace sectors. Yet the story isn't just about efficiency, it's reshaping jobs, prompting workers to acquire new digital skills and urging policymakers to rethink education and safety nets. As AI continues to embed itself into the fabric of American life, it raises questions about privacy, bias, and the balance between human judgment and algorithmic decision-making. Which myth about AI do you think needs the biggest debunking? Many Americans believe that AI is a single monolithic entity, like a robot mastermind waiting to take over the world. In reality, AI is a loose umbrella covering countless specialized tools, some as simple as a spam filter, others as complex as a self-driving car. The misconception that AI instantly replaces human workers also falls flat. Most systems automate repetitive tasks, freeing people to focus on creative or interpersonal work. For instance, accountants now use AI to scan receipts, but they still interpret tax law and advise clients. Another widespread myth claims that AI decisions are always objective. Yet models trained on historical data can inherit biases, leading to unfair outcomes in hiring or lending. The truth is that AI mirrors the data it learns from, and without diligent oversight, it can amplify existing inequities. By untangling these myths, we see a clearer picture. AI is a powerful set of tools shaped by human choices, not an autonomous overlord. Understanding this nuance is crucial as society navigates the next wave of innovation. With misconceptions cleared, where will this technology head in the coming decade? Looking forward, the next 5 to 10 years promise AI that's not just smarter, but more collaborative. Researchers are racing to build foundation models, massive neural networks trained on diverse data that can be adapted to countless tasks with a single prompt. Think of a digital Swiss Army knife, one model that writes code, drafts legal briefs, designs artwork, and even helps compose music. At the same time, advances in neuromorphic chips aim to mimic the brain's energy efficiency, allowing AI to run on tiny devices without draining a battery. This could bring true on-device intelligence to wearables, medical implants, and autonomous drones, reducing reliance on cloud servers and enhancing privacy. Policymakers are also drafting regulations to ensure transparency and accountability, responding to public concern over deepfakes and algorithmic bias. In the United States, bipartisan bills are emerging that incentivize responsible AI research while protecting workers displaced by automation. Education will adapt too. Curricula from high schools to community colleges are integrating data literacy and ethical AI design, preparing a generation that can shape the technology rather than be shaped by it. If these trends hold, AI will become an invisible partner in problem solving, from climate modeling to personalized medicine, deeply woven into every sector of the economy. From a cramped garage experiment to a multi-trillion-dollar engine powering daily life, America's accidental launch of the AI revolution shows how curiosity, risk, and a little serendipity can reshape the world. The journey teaches us that breakthroughs often arise from unexpected corners, a simple activation function, a surplus of data, a daring investment. As we stand on the cusp of even more transformative AI, the real question becomes, how will we, as individuals and as a society, choose to guide this technology? If you found this story eye-opening, share your thoughts in the comments. What AI development excites or worries you the most? Give the video a thumbs up to help others discover it, and don't forget to subscribe for more deep dives into the forces shaping our future. Your voice matters, so join the discussion below and stay tuned for the next adventure.